Hello there, welcome back once again. Now we're still in probability, but what are you looking at a probability? We're going to look at contingency table. Have you heard of what contingency table means? It's another way of representing probabilities, what is happening, okay? And you have probably seen that, okay? With a report, when they write a report or summary, it will be kind of a table. But we call those contingency table. But ask yourself, why not say table? Why do you say contingency table? Yeah, we call them contingency table in statistics. Let's see what it looks like and let's define it. So, another way of representing possible outcomes of an experiment is using two-ways contingency table. So two-ways contingency table are tools of keeping records of counts or percentage and probability problems, okay? You probably have seen that, yeah. Reports, especially the COVID report, they put tables. That's another example of contingency table. So two ways contingency table are especially helpful for figuring out whether an event is dependent or independent. Do you remember independent or dependent? Are we together? Does it mean if I don't social distance, will I get COVID-19? Is that dependent or independent? Yes, if you don't, the chance of you getting COVID-19 is high. By staying at home and social distancing, does it mean I'll get COVID-19? It doesn't mean I won't get it, but the probability staying at home, yes, can affect the chance of me getting it. Are you all together? That's how one uses those statistical independent. They'll collect data and study and come to a conclusion. Fantastic. So let's look at a table, a two-way contingency table. The table below shows the results of testing two different treatments on 240 fruit trees which have a disease causing trees to die, okay? So what it means, they tested trees, 240 trees, because they found that some of the trees are actually dying because of certain disease. We don't have the money or the finances to test each and every tree. What do? A sample. A sample of 240, we test on 240. And from 240, we can draw a conclusion. There's no way also, if you look at even COVID-19, to test each and everyone in the country. You do with a sample, from a sample of 240, then we can draw some conclusion. Yes, the bigger the sample, the better your conclusion, or the reliable is that conclusion. Okay, so treatment A involves a careful removal of the infected branches. Okay, that's the treatment A. Treatment B involves removing infected branches as well as spraying the tree with a chemical. So you're going to remove it and spray with some chemical. All together. So let's see our table. What does our table mean? So our table shows treatment A and treatment B. Then, number of trees that die within 4 years. How many trees dies within 4 years? Then also, number of trees that live beyond 4 years. Are we all together? We can see treatment A there, we have 70. Numbers of trees that dies within 4 years. Numbers of trees that lives beyond 4 years is 50. And treatment B, nothing recorded. But what do we have? We have the total here. What is the total? The total is actually that number plus that number. Treatment A plus treatment B. You can see that, which is 90. So we can actually find that number, which should be what? 20. Because 70 plus something to give us 90. What is that number? 20. Also here, we have 50 plus something to give us 150. What must we add there? Surely we should be adding 100. We're adding 100. Then what do we get the totals here? We can get the totals by completing the table. 70 plus 50 will give us 120, and here we'll add the two numbers there to give us the total. Okay, let's see what do we get. So the first thing is you have a contingency table. Yes, someone will go research, but you might find that the contingency table is incomplete. Yes, I can complete it. How do we complete this? So let's see. Number one, we are going to fill in the missing values on the table, which you've done so far. After that, calculate what is the probability that a tree receive treatment B. Because remember, we have two treatments, A and B. So at random, any tree can receive any treatment, A or B. Are we all together? So what is the probability that a tree receive treatment B? Are we all together? What is the probability that the tree will live beyond 4 years? And our fourth problem, what is the probability that the tree is given treatment B and lives beyond 4 years? Then our last question, are a tree given treatment B and living beyond 4 years independent events? Justify your answer with a calculation. Okay, let's see. So we complete our table. If we complete our table, this is what we get. We have 20 there, we have 100 there, and we just add rows. We add the first row, we get 120, we get 120 also here. Together 240, we add 120 plus 120. We get 240. So if you completed your table, sometimes the table is incomplete, you can complete it. And if you have a complete table, you can start by calculation. Let's see. Now, the question now is, the probability that we receive treatment B, a tree receive treatment B, that will be what? Receive treatment B, how many in treatment B? Over the total numbers of trees all together. So treatment for B is 120, which is conducted on trees, B. The total altogether is 240. So we go what? 120 divided by 240. We get a half, which is 0.5, 50% altogether. Then the second question, what is the probability that the tree will live beyond 4 years? Live beyond 4 years, we'll have to look at what? Notation important. Probability lives beyond 4 years. So live beyond 4 years over the total altogether. Live beyond 4 years. Where is that? The numbers of trees that lives more than 4 years. It's on our table is there. What? It's 150. That's the total. Over what? The whole total, which is 240. And simplify that, we get 5/8. You can leave your answer as a fraction, or you can write decimal or percentage. Okay? Then problem 4. What is the probability that a tree is given treatment B and lives beyond 4 years? We want to give treatment B, but live beyond 4 years. So this will be what? The probability given treatment B and lives beyond 4 years. So this will be the number given what? Treatment B and live beyond 4 years, which is what? Number given treatment B, there's treatment B, living beyond 4 years, that will be what? 100. That's the number there. Can you see that? That's the intersection between treatment B and living beyond 4 years. And we divide by the total, which is 240. And we get 5 out of 12. Okay. Then our last problem is, are a tree given treatment B and living beyond 4 years? Independent event. Justify your answer. To show that two events are independent, you have to show that the probability of A and B is the same as the probability of A multiplied by B. So what we have to show here is that the probability of tree given treatment B and living beyond 4 years is the same as the probability of given treatment B multiplied by the probability of tree living beyond 4 years. Let's see what it looks like. So what you're going to do is this. The probability of tree given treatment B and living beyond 4 years, we've calculated some of them here. It was 100 over 240. Then the probability of tree given treatment B, we're together. Tree given treatment B, where's treatment B? There's treatment B there, which is 120 over 240, which we have it there. A tree lives beyond 4 years. A tree lives beyond 4 years. How many? It's 150 over what? 240 altogether. And we multiply this, we get that this is 5 over 16. But we can see that 5 over 16 is not the same as 5 over 12. You have to state that. 5 over 12 is not the same as 5 over 16. Why? Therefore, the two events are not independent. We just had to show that event A and B is not equal to probability of A times B. Are we together? Then we conclude this is not independent. Okay. So let's look at our summary. So we've looked at tree diagrams. So tree diagrams, very important. You have to look at what? Replacement and without replacement. And that will affect your sample space if you replace or you replace. Are we together? If I replace, if I have 10 balls, we'll still 10 balls inside. If I don't replace, the size gets reduced. We've looked at independent event, independent, and contingency table. Okay. Cheers, guys. This is bye from us, and we hope that you enjoyed, and we hope to see you soon.